Okay. Welcome everyone to our webinar. I am Katerina Galitskaya, Senior Antenna Engineer at Radientum. And today I will talk first about hybrid solver. We'll explain a bit what is it, because based of a demand, just showcasing how we can use it not enough. We need some explanation first, because maybe not so many people even know that there is such a functionality. So hybrid solver is efficient solution for electrically large models with small details that are not feasible to be solved with a single solver. It decomposed the big volume into sub-volumes, so small features can be simulated accurately, and the full model can be can use more relaxed mesh settings. And on the next slide, there are two types of coupling available for when setting the hybrid solver. And unidirectional settings show source to platform coupling only, and bidirectional settings shows iterative source and platform coupling. In addition to well-known time domain and frequency domain solvers, we can use more fitting solver for large-scale simulations, such as asymptotic and integral equation solver, for example. On the next slide, we can see more in detail what is asymptotic solver. Asymptotic solver is a ray tracing solver, which is efficient for extremely large structures, where a full wave solver is not maybe necessary. The asymptotic solver is based on the shooting bouncing ray method, and it's capable of tackling simulations with electric size of many thousands wavelength. On the next slide, we can see the integral equation solver. This is another solver for this large electrically large models, and this is already 3D full wave solver, and it's based on method of moments technique. The integral equation solver uses a surface integral technique, which makes it much more efficient than full volume methods when simulated large models with a lot of metal and a lot of empty space. The integral equation solver includes a characteristic mode analysis feature, which can calculate the modes that's supported by a structure. And on the last slide of this introduction of hybrid solver, this is basically the setup. So the setup is very easy. It does not require any extra time. So it starts with creating an empty sheet. So you can see the step one. You can use either schematic or assembly. And then on the step two, you import all your models. So here is this example, which I will share later after Mikko, of millimeter wave simulation. So you can see here I have 3 different domains, the car, radar, and antenna. So they are 3 independent projects, and then I apply them, import them all into this assembly, for example, or schematic empty sheet, and I have this setup for hybrid solver. And then on the next step, you choose, as you can see, simulation project, hybrid solver task, and you can choose either unidirectional, bidirectional solver, as I explained before, unidirectional for source to platform coupling only. So it's very good for approximation. For example, for antenna placement, it's very convenient. You don't need bidirectional solver for antenna placement. And then you can also have a bidirectional for coupling both ways. And then let's go on to the next slide to sub-6 example. This is, first of all, let's talk a bit about sub-6 frequencies in automotive applications. So sub-6 frequencies enable a wide range of functionalities in automotive industry, like vehicle-to-vehicle communication, which allows vehicle to communicate with each other, infrastructure, and even pedestrians in some cases, or positioning and location, which heavily based on GNSS, or 3G, 4G, sub-6 GHz, 5G applications, or comfort vehicle access with such technologies like remote keyless entry or low power Bluetooth. And the list continues for much more applications. And yeah, on the next slide, we can have a look on the most recognizable automotive antenna. I think everybody knows what is this. It's the shark fin antenna for cellular connectivity. It can actually combine a lot of different radio inside, but this is just for cellular in this case, just to showcase for you. And of course, simulation play a crucial role in optimizing the performance of this type of antennas, as it is mounted on top of a big metal structure. Through simulation, we can analyze and evaluate various parameters, such as like antenna, how antenna radiates, the impedance matching, and find the optimal antenna placement. And on the next slide, we can see that there are two ways to simulate the shark fin antenna. So first one is everybody knows how to do it, using one model, one solver. In this method, you just basically open the simulation software and you do everything in one project, in one file. This model usually is rather simplified because you cannot spend a lot of time to simulate small features, because the size of the car is on this frequency 10th of lambda, and this approach, it may seem very straightforward because, yeah, as I said, you just open the software and you start right away, but it does not allow flexibility and requires a lot of computing resources. And every change that you make in antenna or in antenna position of the antenna or in the car, you need to resimulate everything again. The assembly method that's shown on the left involves assembling a model that incorporates various components, such as vehicle structure, antenna element, and surrounding environment. Assembly allows using of hybrid solver, which combines different simulation techniques to accurately capture electromagnetic behavior and interaction within systems. This approach offers a general view of antenna systems performance, considering its integration into a larger automotive context. So we split the big structure into domains, like I explained in the beginning. What is the principle of hybrid solver? So in this particular case, we split into two: car and shark fin antenna with the cover, with the radome of the antenna. And on the next slide, you can see that I have run the model into two settings using the assembly that I just explained with the shark fin antenna simulated with the time domain solver, and the platform or car in this case simulated with the asymptotic solver. Using the field from the time domain solver from antenna. And the second approach is the whole car with antenna as one project, one model with the time domain solver. However, I still used somehow relaxed model the car and machine as well, because the time can go forever with this kind of simulation, the simulation time. And you can see results in a table. So besides the obvious win in time, we can also win in total amount of mesh cells and therefore decrease memory usage. So on the next slide, we can see a comparison of radiation pattern cuts at 2.6 gigahertz on the high frequency of that antenna. And and this comparison of two methods. So the one model one solver and assembly plus hybrid solver. So the thing with the asymptotic solver that you can choose the accuracy level, and in this case I chose the low accuracy level just to run the quick approximation. And usually the biggest difference is noticeable at back radiation, so what you can see, and in null levels, but it can be tackled with the increasing of accuracy of the asymptotic or integral equation solver. And depending on the solver combination that you choose, you can get all these results that listed. So basically, you can get everything that you can just get from time domain and frequency domain solver with the one model and one solver. With the hybrid solver approach, you can get the same results. Also, 2D, 3D far fields. Just fields, representation of fields, as was shown on a previous slide. Efficiency, radar cross-section for automotive radars, it's important. And of course, you can get coupling between antennas. If you have several antennas, you can get that as well. And of course, and the S parameters, that's basic what you can get. So this is all from my side for sub-6 gigahertz antennas.